Hello everyone, myself Aurum Mukwana, Assistant Professor of EC Department at LJ Institute of Engineering and Technology. In previous session, we have finished unit number 3, that is the geostationary orbit. In today's session, we will start unit number 4, that is a radio wave propagation. In this session, we will cover introduction, atmospheric loss, ionospheric effect, and the rain attenuation. Now, first, we are starting the introduction. Now, first of all, what do you mean by a radio wave propagation? And what will be the effect on the satellite communication? As a signal traveling between an Earth station and the satellite must pass through the Earth atmosphere, including the ionosphere, right? As we know that there are different layers of atmosphere. The layer which is nearer to the Earth's surface is troposphere, which is up to 90 kilometer. Then from 90 kilometer to 400 kilometer, there is an ionosphere. And 600 kilometer upwards, there is a free space. Alright? So, when signal is going to be traveling through a different layer of atmosphere, it will cause attenuation. Then, what are the different impairments of this attenuation? First one is the atmospheric loss, second one is ionospheric effect, and the third one is rain attenuation. This graph shows the different layers of atmosphere, right? Now we are first focusing on the atmospheric loss. Now first, what do you mean by atmospheric loss? It is the losses which occur in the Earth atmosphere as a result of energy absorption by the atmospheric gases. So these losses are treated quite separately from those which result from the adverse weather condition. Cause the atmospheric losses. So, to distinguish between these weather-related losses are referred to as the atmospheric attenuation, and the absorption losses simply as an atmospheric absorption. As a signal travels through different layers of atmosphere, few amount of transmitting power is going to be absorbed in the layers of atmosphere. So it is caused the loss of my signal into the atmosphere. So it is called the atmospheric absorption, right? So how it can be represented in terms of equation? The atmospheric loss, which varies with the frequency, as shown in the graph. The x-axis represents frequency in terms of gigahertz, and the y-axis represents the total attenuation, right, in dB. So the attenuation is represented into the atmosphere in terms of equation is AA, that means atmospheric absorption, is equal to the square bracket AA, that means atmospheric absorption 90 decibel, cosec EL. EL stands for elevation angle, right? So this effect is known as the atmospheric scintillation, which can also occur. Scintillation means the spark of light, right? Now, focusing on this graph, that as the frequency is going to be increased, the attenuation is also going to be increased. But we got a two peak at a specific frequency. One is at approximately 22.3 gigahertz, which cause the absorption due to H2O present in atmosphere. And second one is at 60 gigahertz, which cause the absorption due to the oxygen in the atmosphere. So due to H2O and O2, we got a two peak at 22.3 gigahertz and second peak at 60 gigahertz, right? So it is caused by the differences in the atmospheric refractive index. As I told you that atmosphere has a different layer of different layers, and it also contains a different refractive index. And signal travels through a different refractive index, which result in focusing and the defocusing of radio waves, and which follows the different ray paths through the atmosphere. Okay? Now, the ionospheric effect. A radio wave traveling between the satellite and the Earth station must pass through the ionosphere. Ionosphere contains different ions or atoms which are randomly distributed in space, right? So the ionosphere is the upper region of Earth's atmosphere which has been ionized mainly by a solar radiation. So the random distribution of free electrons in the ionosphere cause the absorption of radio wave, right? So this effect includes scintillation, absorption, variation in direction of arrival, propagation delay, dispersion, frequency change, and the polarization rotation. Now, as I told you, scintillation means a spark of light. Absorption means our signal is going to be lost or absorbed in the ionosphere. Third, variation in direction of arrival. That means signal will arrive at specific point at different interval. Propagation delay. Dispersion means a broadening of pulse. And change in the frequency and the polarization. Polarization means orientation of wave, right? So all this effect decrease as the frequency is increased. Most in inverse proportion to the frequency squared, and only the polarization, rotation, and scintillation effect are of the major concern of satellite communication, right? So as frequency is going to be increased, these all the effects are being negligible, right? To overcome the absorption due to the ionosphere layer, we need to increase the frequency. Now, the last one, that is a rain attenuation. A rain attenuation is function of rain rate. By rain rate is mean the rate at which the rain water would accumulate in the rain gauge situated at the ground in the region of interest. So this percentage time is denoted by P. And the rain rate is represented as a RP. So if you want to find the attenuation into the rain, then it is represented with this equation: alpha is equal to A into RP raised to B, dB per kilometer. Over here, RP stands for rain rate and small a and b depends on the frequency and polarization, right? But this is a dB per kilometer. If you want to find the total attenuation, then this alpha is multiplied with the length, or you can say effective path length. Okay, so we will get the total attenuation capital A is equal to alpha into L dB, right? The L is effective path length of the signal to the rain, because the rain density is not uniform over the actual path length. So the effective path length must be used rather than the actual length, right? So over here, chapter number 4 is finished. These are the references that I have used. Thank you.
So overall, we can say that the radio propagation is the behavior of radio wave as it travels, or you can say propagated from the one point to another point, right? Or we can say that as a form of electromagnetic radiation, like our light waves. These radio waves are affected by a different phenomena like reflection, refraction, diffraction, absorption, polarization, and the scattering. So these several different types of propagation which are used in our practical radio transmission system are line of sight. That line of sight means a radio waves which travels in the straight line from the transmitting antenna to the receiving antenna. Like it is used in cell phones, cordless phones, walkie-talkies, as well as a wireless network, radar, in television broadcasting, also in satellite communication. Satellite communication means in satellite televisions, right? So the line of sight transmission on the surface of the earth, which is limited to the distance, that means a visual horizon. So we can say that it depends on the height of the transmitting as well as the receiving antenna. But this line of sight propagation is the only method which is possible at the microwave frequency, at higher frequency in terms of gigahertz. But at microwave frequency, the moisture in the atmosphere, that means rain, will also degrade the transmission. As we have seen that because of the atmospheric absorption, ionospheric absorption, as well as the rain attenuation will also affect on our radio signal, because a signal is traveled to a longer distance as satellite is in the space and our earth station is onto the surface of the earth, right? So while transmitting any signal, we are always focusing on which frequency we are going to transmit. That means at lower frequencies like a low frequency, medium frequency, and very large frequency. But due to diffraction, radio waves can be bent because of the presence of obstacles. Which obstacles are there? The obstacles are like hills, or you can say mountains, in which it will travel beyond the horizon as the surface wave, because surface wave covers the contour of the earth. So these waves are basically called the ground waves, and these are used for AM broadcasting.